Okay, chapter 2 deals with one-dimensional motion of objects or point particles. And as the name of the unit suggests, this motion takes on a line, and we usually call this line x. And we have to choose an origin for the position measurements, and we put 0 value in here. And usually the right side of the origin is the positive x direction, and the left side is usually called negative x direction. So we put positive values and the negative values toward right and left of the origin. For describing the motion, we also have time recordings. For example, we have an object. It starts its motion at x is equal to 1 meters. It continues toward right, and it is at 3 meters at 1 second. It is at 4 meters at 2 seconds, and it goes back after 2 seconds in the negative x direction. It comes to x is equal to 2 meters at 3 seconds, and it comes to x is equal to minus 1 meters at 4 seconds. So this is a very simple example of motion on a line. You may wonder what the kinematics is. Kinematics deals with the motion only, not its causes. It usually deals with the trajectories of the objects. And here you see the units of chapter 2. We will define position, distance, and displacement, and the differences between this, for example, the position and distance is very important. And we have speed and velocity, also the difference is important in kinematics. We will define instantaneous velocity, acceleration, and a particular type of motion which takes on the surface of the earth. It's a constant acceleration motion. And we will close the chapter by analyzing freely falling objects. Okay, before describing anything, we must first set up a coordinate system. Since we are dealing with only one dimension, we are using only one line for our coordinate system, and the direction of the line, the direction of the arrow, points or indicates the positive x direction. That means if you are going this way, you are increasing your position. With respect to origin, of course, we have to first pick up an origin, x is equal to 0 position. Any mark on this line defines the position of the object. For example, xi in here is the position of this boy, and xf is the position of the same boy another time. So this makes our coordinate system and its markings. Okay, now define distance. Distance is the total length of travel. For example, if you drive from your house to grocery store and you go back to your house again, you have covered a distance of 8.6 miles, just twice the distance between your house and grocery, because you cover this part of line twice when you go from your house to grocery store and go back again to your house. I want to add one important property of distance, and distance is always a positive quantity. It's an absolute length measurement, and it's always positive. It can never be negative. Okay. Displacement is the change in position. It is mathematically defined as the final position or the final distance measurement of your position with respect to the origin minus your initial position. So if you derive from your house to the grocery store first and then to your friend's house, your displacement is minus 2.1 miles. And let's do it. According to the definition, the displacement of your driving, well, the final position is your friend's house, and your friend's house is located at x is equal to 0 at origin. So the final is 0 minus, and your initial position was your house, and this is 2.1 miles. So when you do this, you find your displacement as minus 2.1 miles. Now let's define what the average speed is. The average speed is defined as the distance traveled divided by the time the trip took. So by definition, again, the average speed cannot be a negative quantity, because distance is always a positive quantity and time of course always a positive quantity. So let's do an example of the motion of this car, a red car, and let's find its the average speed. And the question is, well, if the car goes 30 miles per hour for a time of t1 and for a distance of 4 miles, and after that it continues motion for a time 2 with a speed of 50 miles per hour, again a distance of 4 miles. The question is the average speed of the red car is less than, equal to, or more than 40 miles per hour. So we will go by the definition, and usually we denote the average speed as s, and let's write the definition: the total distance of the car divided by the time, the total time. So to calculate for the total time, first we have to find t1, and t1 is, from the definition, it will be 4 divided by 30. 4 is the distance of the car traveled, and 30 is it's the speed, the constant speed, and it is 2 divided by 15 hours. And for t2, this is again 4 miles divided by 50 miles per hour. It is 2 divided by 25 hours. So it is easy now to calculate total time. Total time is just the addition of these two times, t1 plus t2, and addition of these two numbers is 16 divided by 75 hours. And so with this information, it's now easy to calculate its speed, average speed, and we already know the total distance. The total distance is just 4 plus 4, it's 8 miles, and we divide this by the total time, and what we find is at the end 75 divided by 2 miles per hour. So it's less than 4 miles per hour. Alright. Now let's define what the average velocity is, and it's defined as the displacement divided by the total time, or time takes to make this displacement. And since displacement is your difference, the difference between the final position and the initial position, so you can define mathematically the average velocity as x final minus x initial divided by delta t. This means since displacement can be a negative quantity, your average velocity can be a negative quantity also. And if your starting position and the final position are the same, that means you have a zero average velocity. Even if you travel a distance, a certain distance at a certain amount of time, your average velocity might be zero. Now let's look at the motion of this object on a line on xt graph. Xt graphs are smooth curves, and every point on this smooth curve is uniquely determined by the position of the object at a certain time. The position versus time graphs carry all of the information about the motion of the object. You are able to determine its average speed, average velocity, average acceleration, as well as instantaneous velocity and instantaneous acceleration, the change in the acceleration. All types of derivatives of the motion can be uniquely determined from the position versus time graphs. Now let's look at how do we find the average velocity between any 2 points. First of all, to find the average velocity, we need 2 points, both in x and in time. Of course, in x, let's, for example, choose between the positions 1 and 4. Since these position contains only one time information, and we also have the information at t is equal to 0, the initial time. The position of the object is at 1, and the time that the object is at the position 4 is 2 seconds. So now let's calculate the average velocity, and from the definition we know that this is the final position of the object minus the initial position, and the time of the object, the time recording of the object at its final position, and its time recording at the initial position. Graphically, what we do is we connect these 2 points by a line. Okay, let's connect these 2 points by a line. Alright, and then we continue to make these lines to form a right triangle. Okay, so we now have this right triangle. This is the hypotenuse, and in the vertical direction we have this displacement, because the length of this line is nothing but x final minus x initial, and this horizontal length side of the right triangle is nothing but the total elapsed time from the object going from 1 to position 4. And in fact, you can see that this ratio is nothing but the division of this side to this one. And let's call this delta x, which is the displacement, and this is delta t, and in fact these are can be written here, and mathematically this ratio is nothing but the slope of this line connecting these 2 points, the initial point and the final point. So the graphical representation of the position versus time graph, once chosen 2 points, means that the connecting lines of 2 points, the slope of the connecting lines, is nothing but the average velocity of the object. Now let's look at the average velocity between the point at t is equal to 1 and the point at t is equal to 4. What we do, again, make a right triangle. Okay. First of all, connect these 2 points, this one and this one, by a line. Oops. And again form a right triangle. This one is parallel to the timeline, and this one is parallel to the position. It's not passing through one. Sorry. Okay. Alright, so, but this time, since the final position is behind the initial position, this vertical line, which is parallel to the x-axis, will be negative. And as you can see, the slope of this line is negative because it leans toward left, and the slope will give you a negative value of average velocity because the object is mostly going backwards in x. So the bottom line for the graphical interpretation of x versus t graph is, whenever you choose any 2 points on the curve, the line connecting these 2 points, the slope of the line connecting these 2 points will give you the average velocity of the object. To calculate the average velocity of the object between 2 points, we have to wait some time. But most of the time, we don't care about the velocity of the object, average velocity between any 2 points, but rather we want to know the velocity of the object instantly. So this requires a new definition of velocity, which is the instantaneous velocity. And in fact, it is nothing but the limiting value of the average velocity. You know, delta x divided by delta t is average velocity, and it requires 2 different points, both in position and time. But for instantaneous velocity, what we do is mathematically we just take the limiting value of this ratio when this interval delta t goes to 0. The instantaneous velocity can be best explained by using position versus time graph. And suppose we have an object moving in time and in x direction, having this trajectory, and we want to get its instantaneous velocity right when time t is equal to 1 second, right here, this red point. What we can do first, we may pick up 2 different points in time, an earlier time than 1 second and a later time, let's choose 2 seconds. And since we know how to calculate the average velocity between these 2 points, we can draw a line and just calculate the slope of this line. This will be an approximation of the instantaneous velocity at time t is equal to 1. And this is calculated to be 13.7 meter per second. Now, to get a better answer, we may choose these 2 points closer and closer to the point in question. And again, we pick up these 2 points and just connect them to make a straight line and calculate the slope. We get the average velocity 12.1 meter per second. Now it's a different velocity, but this is closer to the instantaneous velocity in here than this one. So what we do next is picking up these 2 points closer and closer to the point in question and make these lines and calculate their slope. And eventually what we will obtain is this lines of average velocities will be a tangent line right at this point in question. And as you see, this tangent line only touches at one point into the curve, to the trajectory, and this tangent line will of course have a slope, and this slope is 10 meters per second. As you see, you can easily calculate the slope, and this will be the instantaneous velocity in here. So the instantaneous velocity at any point on the curve will be the slope of the tangent line right at this point. So this is a geometrical way of defining the instantaneous velocity. Here in this graph you see an object moving on this blue line. It's the trajectory of this object, and this first green straight line, the slope of this line is nothing but the average velocity between time t is equal to 1 and t2. The second straight line is the slope of the second straight line is the average velocity between t2 and t3. And this green straight line touches only at one point to the trajectory. So that means this line is just, the slope of this line is just the instantaneous velocity of the object right at time t is equal to t3. And remember, the definition of the average velocity was just delta x divided by delta t, some amount of displacement divided by the time it takes to make this displacement. And mathematically, the instantaneous velocity is nothing but the time derivative of the position of the object. And I want to make a remark that the position of the object is a function of time. So the time derivative for this function is always defined. Acceleration is a measure of change in the velocity, and the first concept in the acceleration is the average acceleration. Just like in the average velocity, to calculate an average acceleration we need first of all 2 points, what we call initial and final points, and an information of the velocity of the object at these initial and final points. So if you know the velocities at these initial and final points and the time it takes to this change occur, then the average acceleration will be just the difference between these two velocities, v final and minus v initial, divided by the total time. And since the unit of velocity is meter per second, and if you divide this by second, we will find the unit of acceleration as meter per second square. On the right table you see some acceleration values of some certain events. For example, the acceleration of an object, a freely falling object on the surface of moon, is just 1.62 meter per second square, and this is 9.881 meter per second square, which is 6 times that of the acceleration on Earth, on the moon. And on a typical high jump, or high jump has an acceleration of 15 meter per second square. A bungee jump has 30 meter per second square, which is like 3 times the free fall of the surface of Earth. And for example, if you are curious about what the acceleration of a bullet, a typical rifle bullet, it is very high. It is 4.4 times 10 to 5 meter per second. Before we define the instantaneous acceleration, let's define what the velocity versus time graphs. Just like position versus time graphs, the velocity versus time graphs are just these smooth curves, and every point on this smooth curve is uniquely defined by the velocity of the object, instantaneous velocity of the object, at a certain time. So as you see, this green line is a smooth curve, and this curve is a trajectory not in position versus time graph, but it's in velocity versus time graph. Okay, so that means, for example, if you pick up 2 points, let's say 1 and 2 on this line, on this curve, sorry, and if you connect these 2 points, since there is a change in the velocity, because you go from here to another velocity which is larger than the initial one, there is certainly a change in the velocity, and we know that this change occurs because of the acceleration. And if you connect these 2 points by a straight line, if you calculate the slope, what you get is the slope of this line is nothing but the average acceleration between these 2 points. Okay. Similarly, you can find the average acceleration between T2 and T3 just by connecting them by a straight line and just calculate the slope. That's it. So just as we have defined the instantaneous velocity, then in that case, for the v versus time graphs, or the velocity versus time graphs, if you draw a tangent line at any point on the curve, and if you calculate the slope of this tangent line at the point in question, what you obtain is the instantaneous acceleration at that point. So the instantaneous acceleration is defined mathematically by just the derivative of the velocity with respect to time. Okay, since acceleration is the change of the speed or a change of the velocity of an object, in this picture I would like to explain to you when this change increases the speed or the velocity or decreases the speed or the velocity. So let's look at the first picture, and we have a car and it's going in the positive x direction. As you see in here, we have this line, the coordinate system for our one-dimensional motion, and its speed or velocity is toward right, and this green arrow shows its direction and then the value. Well, the value is we don't know, but the length of this arrow can be a measure of the value of the velocity in this direction. And here, this purple arrow shows the direction of the acceleration, and again, this direction for the acceleration is toward the positive axis, the positive x-axis, or it has the same direction with that of velocity. So in this picture, the car is speeding up, or it's increasing its velocity. Well, the next picture, everything is the same except the direction of the acceleration. Now the acceleration is in the opposite direction to the velocity of the car. So in this case, the car is speeding down. Its velocity is decreasing, or its speed is decreasing. And in the third picture, the car is moving in the negative x direction, as we can clearly see from the direction of the velocity, and the acceleration is toward the positive x-axis. Well, even if the acceleration is positive in this picture, since the direction of the acceleration is opposite to that of the velocity, the car in this picture will again be speeding down, and its velocity is decreasing. But in this picture, again the car is moving towards the negative x-axis with its velocity towards the negative x direction, and also its acceleration is towards the negative x-axis. So since the acceleration and the velocity are in the same direction, the car is speeding up in the negative x direction. So its speed is increasing, or the velocity is increasing. Well, whenever there is decrease in speed, sometimes we call acceleration not acceleration, but it's deceleration. Okay, whenever you see the deceleration, that means the velocity and the acceleration are in the opposite directions. Okay. If the acceleration is constant, the velocity changes linearly, and the velocity versus t graph is a linear straight line graph, and the slope of this graph will be the acceleration. And when t is equal to 0, the velocity is the initial velocity, v0. So v0 is defined as the velocity at the initial time. The expression for velocity, this expression can be derived from the definition of acceleration, in fact. So if we go by the definition of the acceleration, it is time derivative of the velocity, dv over dt, and if we multiply both sides of this equation by the differential time dt, we get the differential in v, the velocity, is equal to a times dt. But the thing is, the acceleration is constant, which means it does not depend on time. So when we take the integral of both sides, for dv, the initial velocity is v0 and the final velocity v will be equal to the initial velocity, the initial time, as we always take 0, to the final time, a dt. It is very easy to take these integrals, and this one is just v divided by v minus v0, and the right hand side is nothing but a times t. So we get the expression for the velocity, instantaneous velocity, for a constant accelerated motion. When you release an object from a certain height, it will fall down with a constant acceleration. It will increase its speed linearly with a constant acceleration, and this acceleration is known as the gravitational acceleration. And the gravitational acceleration is nearly constant on the surface of Earth, although it depends on the location of the Earth. For example, on Ecuador, this has a least value of 9.78. On the North Pole is largest. On average, it is usually taken as 9.81 meter per second squared. And these values are different because of the rotation of the Earth. Here you see the time and the position values of an object freely falling down from a certain height, and we simply took the initial position as x is equal to 0, and the vertical axis is x, and it's the increasing x values. Since the object is released from rest, and according to this reference frame, it is released from the origin, the initial position is 0 and the initial velocity is 0. So the position of the object will be calculated by using this simple formula, x is equal to 1/2 a times t squared. Of course, here a is the gravitational acceleration, and it is 9.81 meter per second square. So you see the calculated values of the position of the object at time t is equal to 1 second. It is 4.91 meters, and v is 9.81 meter per second. It's just the value of acceleration at t is equal to 1, because v is just a times t, and if you put t is equal to 1, you get 9.81. And similarly, you can calculate the velocity and the position values by using these two formulas. T is equal to 2, 3, and 4 seconds. Now, here you see a different kind of vertical motion of an object, which is thrown up in the air with an initial velocity, and this is the trajectory of the object, x versus t graph, if you choose the vertical axis as x. And here the directions are important. Be careful in here. When we choose the surface as x is equal to 0 and the increasing direction of x as the upward direction, in that case our constant acceleration will be minus g, and this is important, and g is always a plus value. It's 9.81 meter per second square. When we choose the upward direction as the positive increasing x, then the acceleration will be minus g. So with this information and this particular type of motion for this object, the x value will be v0 times t minus 1/2 gt square, because the acceleration is minus g. And if we give a special value of v0 as 29.4 meter per second, when the object is thrown up in the air, it will decrease its speed because the acceleration is down and the velocity is up. So acceleration and the velocity are in the opposite direction. Eventually it will stop at a certain height, and it will stop right at the top when time t is equal to 3 seconds if you throw the object with an initial velocity of this particular value, 29.4 meters per second. And of course, after the maximum height, it will again fall down to the earth, and you see the second half of the motion, the trajectory will go back to 0 value at time t is equal to 6 seconds.